There must be some chalk somewhere. So we have a spatial torus, and we're looking at the, well, so these are the periodic ends, which you identify and you get a torus, and you're looking at flux loops which go around the torus. And I described to you how you calculate the spectrum of those flux loops. You take some operators which wind around the torus, these sort of Polyakov loops. You look at their correlations, and if the theory is confining, then the states will be flux loops that wind around the torus. And if you have a nice large basis of somewhat different operators, operators with wiggles and so on, you can get excited states as well. And you do a variational calculation in order to get the excited states. So you do a calculation where you find the best wave functional amongst the operators for the ground state. Then you look at the piece of your basis that's basis of states, that's basis of operators that's orthogonal to that, and use that, and then find the ground state in that, and that's the first excited state, and so on. So while we don't know what is the content of these states, we can calculate the energies ordered, you know, going up in from the ground state to the first excited state, second, and so on. And there are some theoretical expectations. As I mentioned, if you can describe a flux tube, as people have believed for a long time, by some kind of effective string theory, there are various approaches I mentioned. One sort of the Lucia type, where you look at an effective field theory for the transverse fluctuations and look at the operators, higher order derivatives, and powers of the fields, and you effectively have an expansion and inverse powers of L, and then you look at what the general constraints you have tell you about these terms. And the other approach, as I mentioned, is the Polchinski, based on the more recent Polchinski-Strominger approach, which is a more direct, without doing essentially what's like a gauge fixing, to just discuss the string theory in terms of transverse fluctuations. You can discuss the path integral over all world sheets, and you do an effective action for those for that kind of, again, effectively it's an effective action for that, but it's slightly different form. And there's been some recent progress there by Drummond and Haridas and Matlock. And the conclusion of these calculations has been that on general grounds, in 2+1 dimensions, you expect the energies to start off with the term you'd expect to be there, string tension times the length of this string. And then there's a correction, which, assuming that it's in the universality class of bosonic string theory, so that the only massless modes are these transverse fluctuations, you would get this kind of term here, which is usually called the Lucia term. I mean, usually without the n, but just with the 6 minus 1 over 6. So, and then there is this term also now, which is in 2+1 dimensions, has been shown to be universal in this approach. If you go to 3+1 dimensions, you have a universal term which is the same as this. There's a factor of d minus 2 up here, so that's why it has become a third. It's the number of these transverse oscillators. And the next term now has a new coefficient that is unknown. Now that is in the Lucia approach. If you take the Polchinski and Strominger approach development, then and Drummond showed, and later Haridas and Matlock, that the next term is in fact has C2, which is exactly the coefficient, same coefficient as here. That is to say, well, apart from same coefficient as there, so that it's in 3+1 dimensions as well. Now, if you take a Nambu-Goto expression, So that's the free string theory. So one thing we do know, and which we'll compare with a lot, is the free string theory expression. So if you're in an Amburgotto free string theory, there you have an energy squared, which is sigma L squared, and then contributions which essentially come from the occupation of various oscillators which create waves along the string. And then there's something for the momentum of the string if you do have a non-zero momentum. Now, forgetting the momentum for a moment, if you just take this, and if you take, if you form the energy by taking the square root of this, and then expand it in inverse powers of L, then what you get is precisely, rather, what these predictions here are precisely what you would get if you expand to order 1 over L and 1 over L cubed. So these developments have said that up to order 1 over L cubed, the energies are precisely what you get from the free string theory if you expand the energies. And that's on sort of general grounds, on fairly general grounds, that one believes that's the case, although the arguments are very different in these in the two approaches. I don't think so. No. There's no assumption. Oh, weakly coupled. Well, I don't think so. No. I think it's a very general. It's looking at very long strings. Apart from that, I don't think there is any assumption. It's just I think a long string assumption. No, certainly no weakly coupled. Yeah.
The coupling constant sits in front of this topological term on the world sheet and tells you should only look at Riemann surfaces.
Well, okay, so I don't know. I don't know string theory well enough to.
Maybe the fact it's a long string and you fix the boundary conditions is enough.
Yeah. Somehow when you look in the 1 over L expansion, I mean the way these, I'm most familiar with Lucia's calculation, and there you just have these, you just have a very general effective action for these transverse oscillations. And then you consider these order by order, and then you impose constraints that come from various considerations like open, closed string duality and so on. And you come up with these conclusions. I'm not quite sure, in principle, somewhere there in these high order operators should be the interactions that might be there between strings. And so I suppose, but I'm not quite sure how that fits in with the other language, which I'm sort of much less familiar with. But Drummond's here, so he can.
Well, essentially you consider the spectrum of a single string, so you're not really considering string-string interactions.
The worry would be that single string would itself fluctuate wildly and intersect with itself.
Okay.
Suppress.
Right. Okay. Yeah. Essentially, neither of these approaches have free parameters in. So things like the string coupling constant, I guess you don't see them. So I think essentially you're looking just at the spectrum of a single string. So imagine you were doing string field theory. You haven't put in interactions yet. Something along those lines.
So you're saying that this is like a non-interacting, you think?
Right, yeah. You're just considering a single string in a flat background. What are its excitations? What are its fluctuations?
But surely some of these terms, at least in Lucia's approach, where suppose you put in some very high order derivatives and powers of this fluctuation which look like a complicated interaction term. That is a complicated interaction term in terms of these transverse displacements, which sounds like a interaction of strings with themselves as well.
It's more like a kind of an alpha prime correction, if you like, correction in the expansion in the string tension. So that would be a correction for already at the level of free strings, but just to do with the correction to the large length limit rather than anything else.
Right.
Yeah.
You're not
maybe
summing
you're right.
all world
Yes.
sheets different topologies.
Well, it is always,
That's the question.
Yeah.
So this is, you're just
No, you
looking at
don't.
long wavelength modes. Is that the idea? You're just looking in these approaches?
That's one question, and the question of string interactions is a separate question.
Yeah, I was never really clear how much that was encoded in.
Well, in large N gauge theory, you believe that you don't have to worry about string
That's right.
interactions.
That's right. But
And of course, in your lattice simulations, you're including everything that contributes with those boundary conditions. So.
And we're interested, of course, in not just large n, but also going down to small n. In particular, differences between n equals 3 and large n.
Mm-hmm.
So,
Well, so in some sense, that's your lattice simulation of those different values of n, quantifying how much the interacting string effects change the answer.
Okay.
So one situation where you have a very strongly interacting string is just the abelian. Weakly coupled field theory, but the string interaction is of order 1. So I guess I could rephrase the question and say, do all these formulas apply to a Nielsen-Olsen vortex in the abelian?
Yeah, well, I'd have to think about that. I'm not sure.
Yeah, you say yes.
I'm not sure either about this other. You know, I can see what they do, and they claim it's general, for instance, Lucia. But I'm not quite sure how general. Yeah, okay.
Lucia is universal. Lucia's term is universal. So whatever you do, it's always there.
Yeah, so that's right, but the actual approach that they take of looking at
Doesn't matter. Doesn't matter.
no, that's universal, but we're thinking of going beyond that.
Yeah.
The sort of systematic approach of including, you know, trying to see what is the general possible string theory by looking at higher and higher powers in 1 over L, which come from these higher order interactions between. I don't know. Is that actually a completely general approach to the string?
Oh, I don't.
And that's what I'm not sure about that. So I thought it was. Or at least I thought they were claiming it was, and it looked like it was. When you formulate it as a field theory in terms of transverse displacements, it's hard to see it as other than general. On the other hand, it's always polynomials, of course, of these things. Okay. Well, let's see what. So at the moment, what we have is that these approaches do say that things look like the Nambu-Goto string up to order 1 over L cubed, and this is. So what I'll be comparing with actually is a Nambu-Goto formula, because that's a nice, as well as those other expressions. So that's a nice complete expression for the free string theory, which has been remarked, you know, several times. It's if it's going to be it's going to be valid anywhere. But if it was going to be valid anywhere, it could only be valid at n equals infinity, because it's only at n equals infinity the strings don't interact. So that's so you would expect maybe that it gets better at large n, perhaps, if it is any good. So here you have the energy squared, you have this term, and then you have the a term which involves, so you have these oscillations of the string which you quantize, and they involve frequencies which themselves are quantized because the string is periodic with length L, so it's 2 pi k over L, the energy and momentum, and the momentum can either be flowing one way or the other, so I call them left and right-handed, and if you sum up the occupation number of the different modes k, and then you get a big integer, which you can so k is actually, it's e to the momentum is actually 2 pi k over L. So k here is an integer. And so you have this expression here, so the energies depend on how the different modes have been filled, the number of times you've put in a creation operator with a particular mode onto the string. So it's really the occupation number of these different modes, the number of phonons of a given momentum, and that all adds up to this particular energy. And this is the 0-point energy from all those oscillators, which you subtract, and which gives a sort of famous Lucia term. And then there is, if you give momentum to the string in addition, you'll get if this is you'll get a contribution from that. So this goes back to Arvis in 1983, and it appears sometimes in this complete form, sometimes in truncated forms in various string theory books. So that gives us something to compare against. Of course, I would very much like if someone had some interacting string theory and gave me a spectrum that I could compare to as well, but I haven't been able to find anything like that. The only thing we find anything really a nice closed form is for the free string theory. Maybe that's no surprise, since you can't in general solve the whole spectrum for interacting field theories. Why should you be able to solve it for interacting string theories? So that's so before I actually go to the actual results of some of the calculations, let me tell you about the kind of calculations people have been doing that are related to this. Just name a few, because I'm really taking a particular approach, which is to look at this closed string spectrum. there's been a lot of interesting work looking at the actual potential between static sources as well, recent work. Of course, old work as well, but I just give you some recent references. So there have been some people who've been doing very accurate calculations in 3 and 4 dimensions for the potential in both in SU3, SU2 and SU3, but also Harvey Mayer has looked at SU5, so people are looking at larger n at the same time. There have been some algorithmic improvements that have made it possible to do very accurate calculations of these quantities, much more accurate than in the past. So that's one approach, and I'm not going to really discuss this. I think they're very interesting things to learn, and I could tell you something about what people have done, but I don't have time, and I won't do that. So I will be talking about flux tubes wound around a spatial torus and the whole spectrum there. Here, most people have looked at the ground state, although now there is at least one calculation that starts looking at the excited state. There were old calculations that looked at excited states, but they were very rough. But the sort of modern calculations have mainly looked at the ground state, what you would call really the potential rather than excitations of the potential. Then another approach has been to look not at energy spectrum, but to actually look at the values of the Wilson loop and compare those to what you expect from Nambu-Goto. Because in Nambu-Goto, I showed you expression for the spectrum, but actually you also have expressions for Wilson loops. They carry the same information. A Wilson loop is, if you like, as I showed you, it's a kind of correlation function, or say Polyakov loops. It involves a sum over all energy eigenstates, so exponentials of energies times some coefficients. And in Nambu-Goto, you can calculate that as well separately. So there are some nice expressions for that, and you can see that in some of the papers. This is actually a slightly old paper, but I didn't have at hand. I suddenly lost my reference to a newer paper, so that's the one I gave. So, okay, putting that aside now, just to let you know there is more out there than what I'm going to tell you about. Let me focus on this particular approach, which is to look at the closed string spectrum. And I will do it in 2+1 dimensions, at least that's what I will show you here, because that's where I have accurate calculations. There are some calculations in 3+1, but they're somewhat less accurate, and we are actually doing calculations in 3+1. And I think from the first results we've had that things are not going to be that different. The conclusions will not be that different, that is to say. 2+1 dimensions is a theory in which we believe we have linear confinement. It actually has, at the perturbative level, the Coulomb potential is logarithmically confining, but there is a non-perturbative physics that we don't understand which produces linear confinement. The coupling in 2+1 dimensions is now dimensionful, so G squared has dimensions of mass, and what that means is that if you're doing any perturbative expansion of some process on a scale L, it will be in powers of G squared, but you need something that's dimensionless, a power of something dimensionless, so it'll be compensated always for by a power of L. So really the effective dimensionless coupling you have in the theory is the scale you're looking at, L times G squared. That's the way it'll always work out if you do any kind of calculation. So what you have is a running coupling that goes to zero extremely fast at short distances. And that's also reflected in the fact that this theory is super renormalizable. You don't have any relevant divergences, so you don't have these logarithms and things that you normally find in 3+1 dimensions. Although that's a slightly different behavior than you have in 3+1 dimensions, it's qualitatively the same behavior of ultraviolet freedom and coupling becoming large at longer distances in the infrared slavery, if you like. So, so what we're going to do is to look at these flux tubes around this torus. And as I've already told you, there is a minimum length that one can look at. So this is the length of my torus and my flux tube. I've described this as a spatial torus. However, that's just a name, and I can equally say, well, what do I learn if I think of that as being time? Label this as time, and the other three directions are now I label as space. Then clearly I'm at finite temperature. This will be a finite temperature system where these are the Polyakov loops in the finite temperature system going around the time direction, and T is equal to 1 over L. And I know that when I make L smaller and the temperature higher, at some point I encounter a phase transition, which turns out to be for larger n, or n larger than 2, in fact, for n greater than or equal to 3. It's first order, sorry, in 2 plus 1 dimensions, it's for n greater than or equal to, certainly in n greater than 4, you will have a first order transition. I mean, SU4 is a bit tricky. So what you have is you have a deconfining transition, and at the deconfining transition, after the deconfining transition, this string can break and has an overlap onto the vacuum. So you no longer have, these operators no longer overlap onto strings. So you no longer have strings going around this torus. So what this aside tells you for now is that actually if I go back to calling this a spatial torus, if I'm on a finite volume, there is a finite volume transition, phase transition. If I shrink one of the spatial tori, keeping all the others large, I will go through a phase transition, which is really just the same as the deconfining transition after a relabeling of axes. So
why does the behavior depend on the dimension and n of the SUN? Whether or not you have a phase transition and whether it's first order?
why? I'm now talking about the gauge theory.
Or even how do you see that it does depend on these things?
Oh, well, what you do is something very pedestrian if you're a lattice theorist. You do SU2, you do SU3, and you do each group separately, and you do calculations of the, precisely calculations of the effective string tension as a function of temperature, or you look for a phase transition. And you find that in SU2, for example, or SU3, that you have a phase transition. For instance, there's a diverging specific heat at some temperature, and you find that, but you find it's continuous. That is, and you find that there's a mass that goes to zero there, continuously. So it's a second order phase transition by the sort of, at least on the face of it. And then when you look at something like SU5 or SU6, you again find, what you find is that as you increase the temperature, at some point there's a jump in the internal energy, in the effective action. There's a jump to another state. There's actually a discontinuity. So it's a first order transition. So you actually see these things explicitly. Sometimes there is a little bit of difficulty in deciding what is the transition or what is the order of the transition. But certainly for larger n, it's very clearly first order, and for SU2 or SU3, it's very clearly second order. SU4 is a tricky case for various technical reasons that one of the participants of this workshop, Philippe Dufourcron, could tell you a great deal about. He's an expert on these things. So, yeah, so it's an explicit calculations that one's doing.
Is there any theoretical understanding of these finite volume transitions? Why they depend on them?
Why they depend? Yeah, there are. Okay, I don't really want to talk about this, but there is there are various theoretical understandings. First, part of it is based on the idea that an order parameter for these transitions is the Polyakov loop. And and if you go into the deconfined phase, so and the Polyakov loop looks like, in a sense, it's something which is which can take values. If it may be zero, but if it's not zero, then its typical values belong to the center of the group, and that's because there is a symmetry. If I'm on, it's easy to see on the lattice also in the continuum in a slightly different way in terms of gauge transformations that are periodic up to an element of the center. But suppose I'm on the lattice and I multiply all the links here by an element of the center. Now in the plaquette I will get Z here, and from this plaquette I will get Z and Z star, and since Z being an element of the center commutes with all the other matrices, I can bring them together and give you 1. So the plaquettes are not changed. The value is unchanged if I multiply all these links by an element of the center. The measure is not changed. The Haar measure doesn't care if you multiply things by an element of the gauge group. So these things would have exactly the same weight in the partition function. The field configurations after multiplying an element of the center have the same weight as the ones before. So it's a symmetry of the theory. And if you have any contracted loop, like a glue ball, well, you think of it as a contractible closed loop or flux or something, and that's the kind of operator you would use. The net number of these links it has is 0. It has an equal number going this way to an number going that way. So that also is not changed under this transformation. However, Polyakov loops are changed. They go through the net number once. Even if they have wiggles on them, they go through a net number once. And so the Polyakov loop will go to Z times a Polyakov loop, while a glue ball operator doesn't. So that's immediately also why, so actually the center symmetry is related to confinement and deconfinement. And you can see that because suppose I ask whether there is it possible for glue balls, for this kind of state to turn into a local glue ball. That would be a deconfining situation where you can break the tube and it turns into a local contractible loop. That would require, so you'll be looking at this operator times glue ball operator. And if that was non-zero, suppose that's equal to some value C, non-zero value, then if I do this transformation, I pick up a factor of Z here, but nothing from here, so it would go to, under this Z transformation, it would go to Z times C. So that's a different value. And if this symmetry was good, that's not possible. Therefore, the only value you can have when this symmetry is actually good is if this is 0, where you have a 0 overlap between these operators. The other possibility is that this symmetry is spontaneously broken, and that corresponds to having non-zero values. So spontaneous breaking of the symmetry goes along with, this is one of the ways of saying this. There are other ways to do with thinking of this as a free energy of the quark and so on. But basically, so the Polyakov loop, and the same is true for the expectation value of the Polyakov loop. If the expectation value of the Polyakov loop was something non-zero, say C, some constant C non-zero, then if I do this transformation, I get Z times C. And again, that would not be possible because this should be equal to itself by saying that this should be equal to, if the symmetry is not spontaneously broken, it should be equal to this. So if it's not spontaneously broken, this symmetry, Polyakov loops have 0 expectation value and no overlap onto contractible loops like glue balls. While if it is, if you have spontaneous breaking, then this will be non-zero, and that will be the deconfined phase, and so on. So, okay, so this is not a. I'm not sure if this goes halfway to answering your question, which was. But I wanted to say actually this at some point anyway, because and it's good that you asked me this, because this is a way of counting. The center symmetry is a way of counting the number of times you wind around. And in a continuum, what you would have, of course, you don't have lattice things, but what the typical thing you would do instead is you would say that you have periodic gauge transformations up to an element of the center, and that would have the same effect on a Polyakov loop. That would have the same effect. You would, this path-ordered exponential of the gauge potential would pick up that element of the center, while any closed loop would not. But on the lattice, it's quite explicit. So there is the center symmetry whose spontaneous breaking follows. Now, the specific thing you asked, well, okay. So these Polyakov loops you can think of when they're non-zero as existing in the elements of the center. And then you can say, well, let's think of an effective theory of that kind. This is an effective theory which now lives not in, say, 2+1 dimensions, but you're now thinking of this as being just a number, so it's in 2 dimensions. So you're looking at theories in 2 dimensions that are essentially spin theories, Zn spin theories. And those have phase transitions, and you would expect that if you have a second-order phase transition here, and a second-order phase transition in this 2-dimensional spin model, they should have the same critical exponents, so you have some kind of relations there. So there are these Svetitsky-Yaffe conjecture that when you look at a phase transition, and if it's second order, you can say something about its critical exponents. Well, you can say things precisely about its critical exponents by looking at a theory in 1 dimension lower that where the Polyakov loop is in the appropriate center of that of the group you're looking at in higher dimensions. If it's SUN, it will be Zn. And then there's and then, of course, you can also then discuss, in some cases, of course, when the things become first order, you can discuss the order of the transition by looking at these spin models and considering various effective interactions you can have with respect to symmetry. And these spin models are much simpler, and you can discuss the expected. And sometimes that gives you some idea. That gives you some idea of whether you expect, not a complete idea, but it gives you some, you have some expectation whether you expect a first order or. Though I must say that it led to, depending what you put in these effective actions, people came up with there were controversies about whether it should be second order or first order at various times during the last 15 years. But there are these ways of analyzing these transitions. Certainly if it's second order, then you can say something about it. You can relate its critical exponents to a lower dimensional spin model. If it's first order, it's a bit trickier. So people look at these effective actions and say something. But I mean, you know that Zn, you have things which are invariant on the Zn symmetry, so you would have n of these spins or something of that kind when you put together terms. Okay, let me move on. So what we have is a situation where we can look down to some minimum length, and beyond this minimum length, we should have strings in the spectrum of strings. And it'll be interesting to know what that spectrum looks like. So here is a first glance at the ground state. So here's the result of a calculation in SU5. That's for me reasonably large n. I mean, 1 over n squared is 1/25th. So corrections are, if you think corrections are as you expect to be order 1 over n squared to the large n limit, then this is certainly much closer to large n than SU3. So what I've plotted here is the energy of the ground state as a function of its length, and I put both in certain units of the string tension. That's sort of reasonable. That gets rid of the lattice spacing. Otherwise, you would have this is a calculation done under fixed lattice spacing, and so otherwise there would be lattice. Everything would be in lattice units, which is a little bit less physical. So instead, I express them in terms of the string tension. Now, this string tension is the one that you obtain from this calculation. So if you look at the long string, it's pretty unambiguous. You get the accurate value of the string tension, whatever the corrections are. The corrections are extremely small because they're some inverse powers of L. So there, from the points which are right at the, which correspond to the longer strings, you can easily extract accurately, with very little errors, a string tension. And then you can use that string tension to scale the lengths of your loops, which are expressed in lattice units. And here it is. It goes from 1 to just over 4 in this case, or 1.3 to about 4. And in this case, this minimum length that I talked about, the length that you wouldn't be able to go below, is about just over 1. It's around here. So we're getting very close to the very minimum length that we could consider. Now, I've also scaled this by the square root of the string tension, which is maybe less obvious. I'm not sure that was a good idea, but anyway, it doesn't really matter. It does get rid of the lattice units, but it's not the obvious scale to use, perhaps. Anyway, so we have, so this is how it looks, and the first thing you see is that it is, obviously it looks as if it's roughly rising linearly. It's not exactly linear because 0 is here. So if you just had sigma L, it would be some straight line coming up from here, and it's clearly missing it as you go down here. It's heading towards 0 faster than it should if it was just linear. And if you now try to fit it with various corrections, the dashed line is the one where you just put in the Lucia correction. And that does a good job of getting some of this deviation from linearity. But then it starts failing significantly. However, if you use a Nambu-Goto, you get pretty much to the points all the way. So this, and the difference between these is that this thing is an expansion of this to first order. So how I could describe to you various ways we tried to make this calculation careful, but I won't do that. If anyone's interested, I can do that afterwards. At this point, let me just ask the question, I've shown you a plot here. These are numerically calculated values of the energies. They have some uncertainty on them coming from the numerical calculation, but the uncertainty is actually smaller. You can't see it here. It's on this kind of plot, it's rather small, and therefore you can't really judge how good is this fit. You know, how good is Nambu-Goto in fitting these points, because my errors, you can't really see my errors here. So let me show you, so let's ask how good is a bosonic string description at this stage. What is the universality class of the effective string theory? What do we learn from this particular plot? To do that, what I'm going to do is I'm going to take the individual, for example, I'll take two approaches, but the first one is to take the individual energies, and here is the expression I just wrote down, except usually I wrote it with C equals 1. C equals 1 corresponds to the bosonic string universality class. If you are with different kind of strings, which have some fermions on them, like Neveu, Schwarz, or Raman, you can get different values. It all depends on what are the massless modes you've got in the theory. You may have some massless fermionic modes, you subtract from that constant. And so there are typically the reason I mention that is typically if you're looking at different universality classes, C would differ by something like 0.5 from one universality class to another. So that's the kind of, if we want to show that C is equal to 1 actually, what we need is to have an accuracy which our values need to be a lot closer to 1 than to 1.5 or 0.5. If they overlap between 1 and 1.5, you haven't really learned much. So that's just to give you an idea of the precision one needs in order to distinguish different universality classes. Okay, so what you do now is, there are various ways you could do it, but just to present the results in one particular way, what I'll do is I'll take my different values for the length of the string, take neighboring values, and fit the two neighboring values of the energy by this functional form here, neglecting any other corrections, just these two terms, and see what is the resulting C effective. There are 2 points, and it will determine 2 parameters, sigma and C effective. So I'll get some kind of C effective. And indeed, it would come, if you just do the trivial calculation, you see that C effective for 2 lengths L and L prime will have this form. So I plug in the energies here, the lengths, and I get a value. So that's one way of getting a C effective. Now, I don't expect, for short strings, there probably are higher order corrections, so you don't expect C effective to be 1. But what you expect as you go to longer strings, as L and L prime get longer, and these corrections die out relative to this, that C effective should be going to the value appropriate to the universality class of the string. Is it 1? Is it 1.5? That's what we want to see. We expect 1 if it's a bosonic string. You can do the same thing using, instead of this, the Nambu-Goto formula. So you take the Nambu-Goto formula, you replace the 1, you put in a C effective here, and you fit it to neighboring points. And I'll do both of those things, and you'll see results from both of them. So if you do that to this particular calculation in SU5 that I just showed you, this is what it looks like, the result. And there are 2 sets of points because there's those 2 sets of fits, one using the Lucia formula and one using Nambu-Goto. So this is what you see. Here is the C effective, and here's 1, 1.5, 0.5, and as I say, these would typically be different universality classes. And the question is, what happens when L becomes large? Well, using the Lucia formula, it doesn't, clearly there's large deviations when you're at short strings, but as you make the string larger, it does seem that it's sort of heading towards, certainly much closer to 1 than to 1.5, these red points. But of course, at some point, as your strings get longer, this correction, which is 1 over L, gets smaller, and you can't determine it so well. So the errors start blowing up. The errors start getting larger, and you lose control of the calculation. But here you still have reasonably small errors, and it is clearly that it is quite a lot closer to 1 than to 1.5. If you use a Nambu-Goto, then actually it's on 1 pretty much all the way, apart from the very shortest string, which is getting quite close to where you lose strings altogether. So that's quite remarkable. I mean, what that's telling you is Nambu-Goto is a good fit all the way, certainly for all these points, and indeed including this point if you're willing to put up with a 2 sigma effect, 2 standard deviations. So Nambu-Goto does fit this whole range pretty much. So what that is telling you is that, okay, this tells you that there are higher order corrections when the string is short beyond the 1 over L. And this is telling you that those higher order corrections to a good approximation are just what you get by taking that Nambu-Goto formula and expanding the square root. So that's actually reasonably remarkable because, you know, we're talking about here, what are we talking? We're talking about strings whose length is 1.5 times root sigma. Root sigma is about, the inverse of root sigma is half a Fermi. So we're talking about strings which are about, you know, 0.75 Fermi long, and their width is probably 0.5 or more Fermi. So these things, if you look at them, aren't strings anymore. They're just blobs. And so why on earth are they behaving like a Nambu-Goto string to this accuracy? Well, I think that's an interesting question. I mean, it's in order to sort of raise interesting possibilities that we do these calculations. And this tells you, I think, that there is something that needs to be understood here. It's not just a naive long string that's behaving like a free string. This is a blob, short blob that's behaving like a free string to a good approximation. So maybe you can see that in a dual approach or something, but it's not evident if you just look at it directly without doing something else. It seems unlikely that that would happen, and yet it sort of does.
It is a feature of things with ADS CFT duals anyway, that the connection between the gauge theory and the string picture doesn't rely on there being flux tubes that are confined. The flux can spread out, and that corresponds to the string drooping into the interior of ADS 5.5, but it's still a string, and it still looks, you know, its excitations locally look like the excitations of the string.
So that's exactly, you know, there may be evidence if one can make that, you know, make a tight connection here between short strings.
It's very hard to make a tight connection because there's no known ADS dual Mills theory.
Yeah, of course. But maybe there's a hint here then of what one should be looking for. So that's, yeah. So it's actually, I think that's a good comment. I think it is, it's not by looking at the thing directly that you would at all believe that it looks like a string. It must be that there is something indirect like a dual which tells you that.
Also in ADS, the effective central charge would be different because it has an extra dimension.
That's true as well, right? Somehow in this context you expect that extra dimension is massive or something. The field has a mass on the world sheet. So there's some potential pushing it towards the bound. Well, it's two effects, right? It can still droop into a certain extent, but there's a potential pushing it back. So you could imagine that it could go to some extent, but there's some mass on it.
So there's so it's not straightforward, but it actually there's some interesting questions here. Yeah. No. Well, the other thing is, maybe I should just show. I didn't want to spend much time on that was larger n. If you look at the other extreme, SU2, smallest n you can look at. Actually, so there the calculations are much faster, and just because from time to time you like to see calculations which are extremely precise, where you don't have to think about the errors very much. We did some calculations for SU2 here in 2+1 dimensions, and you might say physically who cares about something like that, but at very high accuracy with a huge statistics. So that the errors here's the same plot for SU2, a particular example in SU2, and now the error is almost invisible. And you know, here are the Nambu-Goto values, except for a very shorter string where you see within the error is a large deviation. Here you see, you know, it's right on 1, the effective charge, and then of course the errors get larger at some point. While if you use the Lucia formula, as usual, of course, if Nambu-Goto is correct, the Lucia formula has to have large corrections of high order 1 over L, which come from the Nambu-Goto. So this is no surprise. This is not any independent confirmation. So actually, even SU2 shows the same behavior. So
going to small L, that's where it's really becoming stumpy.
Yeah, at small L it's stumpy, but in some sense, you know, L equals 2 is already quite small L. It's not it's not a string like this. it's a string like this piece here, sort of.
So the effective central charge does go up as you go to smaller L.
That's with using the Lucia formula, but if you use the Nambu-Goto, it doesn't actually. This is
These
the
are not
Nambu-Goto.
data points? Or
They're both data points,
yes,
which have been analyzed, one by calculating this effective central charge
Well, the
using...
effective central charge is not just that. That's something you can calculate, and it's as a function of L from the Navigato.
well, that is to say, the way I do it is I take
Oh, I see.
the Navigato formula and I just plug in
Yeah.
a different coefficient here.
Uh-huh.
So this is a Navigato formula with the square root, and I just plug in a coefficient here, and then I solve for neighboring values of L, what this coefficient is and what is sigma. And alternatively, I can do that for the Lucia formula, and you'll get quite different effective central charges. At large L, they should become the same, of course, where all these high-order 1/L collections disappear. So at large L, they tend to the same limit, but at small L, they will have a different behavior. And so basically...
Navigato fits better as...
Yeah, Navigato fits almost perfectly. Not quite perfectly at the very shortest lengths, but down to extremely short lengths, it fits extremely well. So that's really the message from this. It's really the message is really that if you look at the higher order corrections here, they must be dominantly those that come from expanding the square root. That's what this tells us. Okay. Let me move on a bit to excited states now. That was the ground state. So let me move on to excited states. Now, excited states are, of course, going to be heavier. Now, for many calculations, types of approach to calculating things, that doesn't matter. But as you saw in our lattice calculations, we're calculating these numerically correlation functions, and they, as you increase time in your correlation function, it falls exponentially, and up in the exponent you have the energy. So when I'm looking at things which are have a higher energy, my exponential falls more rapidly, and my errors, and it falls more rapidly into the statistical errors. I mean, the statistical errors relative to the signal, if you like, get larger more rapidly. So it's harder to do the calculations once the masses get larger. So what's important, since you can't go far in t in order to see a single exponential, what you need is your single exponential to really start as close to t equals 0 as possible. You want operators which project onto your excited states with close to 100% overlap. And our previous calculations weren't really designed to do that, the ones I showed you there and so on, because they were those standard calculations where the operators were designed to work for the smooth ground states. So now my student Andreas Athanadorou produced a lot of operators which have structure in them, Polyakov loops with wiggles. So these are all Polyakov loops. That's to say they wind once around the torus, but along the way, as they wind, the operators have all kinds of wiggles in the spatial, in a given time slice here. So the time goes this way, you're in a given time slice, and you wiggle the operators. So the hope being that this provides you with a better basis for excited states, which you think of as being in. So this is a kind of intuition that the excited states we're talking about correspond to fluctuations of the flux tube. So it's a wiggling flux tube, and therefore you better use operators which are wiggling. And so these are typical examples. And once you have wiggles on them, you can make them so that you don't have the same wiggles left and right, so you can have negative parity and positive parity states. So typically we had like 1 to 200 operators. These are all smeared as well, so they're not just bare Polyakov loops in terms of links, you've made them thicker with so there are many paths involved effectively in these kind of operators. So, there's a large number of operators here, separately in various sectors, positive parity and negative parity, and also later we'll discuss momentum. So let's look at the first excited state one gets from this kind of calculation. So this is SU. So in this particular calculation, what we did, although the other calculations we did in 2 + 1 dimensions range from SU2 to SU8, in this particular calculation, because it involves a lot of operators, it's quite heavy going for both us and the computer, and so we only did it for in a few cases. So what we did is we did a calculation for a modest value of the lattice spacing in SU3, and then so that we could compare what happens when you increase n, we also did the same calculation for SU6 at approximately the same value of the lattice spacing when expressed in units of the string tension. So there we can compare two different ends, n equals 3 and n equals 6. And then to check whether what we're seeing at this lattice spacing is perhaps continuum physics, we also did another SU3 calculation at a smaller lattice spacing, one which was down by a factor of 2. So basically your whole calculation scales up in lattice units by a factor of 2. So we've got control over some control over the large n limit and some control over the continuum limit in these calculations. Now this is a calculation from one of these, well, there are two SU3 calculations here. So this is the first excited state, again expressed against the length here in units of the string tension. I've now normalized the energy a little bit differently. I've divided it by the string tension times the length, so that you factored out the piece that is growing with L. So if I had looked at the ground state on this kind of plot, it would just be going up to a constant value. Well, it wouldn't be going up to a constant value here somewhere. So this is energy divided by sigma L. Now in this case, the string tension is obtained from the ground state, so it's not a free parameter anymore. We had very accurate calculations for the ground state of this loop. It enables us to calculate the string tension very reliably, and then we use that string tension in any of the formulae which we're checking here, whether it's Lucia or Nambu-Goto. So there's no free parameter at all in any of these fits now. No, zero free parameter. Okay, so what we've got here, we just look at these points. We've got a set of values for different lengths of the energies divided by the string tension times the length. And there's two sets of points, really. Forget this. I don't know why we put this in the plot. But anyway, there are two sets of points. And the red points here, which you can see lie right on top of the blue points, are at the lattice spacing, which is about half this lattice spacing. So when you change the lattice spacing by a factor of 2, nothing changes. By eye, you can see no difference at all. So basically, that means that the dependence we're looking at here for the first excited state is really the continuum limit of the theory. With the continuum extrapolation, you get with slightly larger errors, you get the same values. Okay, so these are really continuum values. That's what one should learn from this. And now let's look what they're telling us at their dependence on L. Well, I showed here three particular fits. The first one is Nambu-Goto. So I've taken, remember that was energy squared time equals something. So when you take the square root, you end up with a square root here for this, and you can pull out the sigma L. So you have this expression. And for the Nambu-Goto, there's, in the Nambu-Goto model, the first excited state with zero momentum along the flux loop corresponds to the lowest one phonon, or if you like, one excitation of the lowest momentum going left and one excitation going right. So the net momentum is 0. So you've got two excitations in there. And they contribute n equals 1 in this normalization. There should have been n left plus n right over 2 here. I just call it n. That's a bad notation because it can be half integer if the momentum is non-zero. But anyway, just to warn you, because later we'll be looking at non-zero momentum. So you have here n equals 1 in the Nambu-Goto. That's what you expect for the first excited state. Sigma has been determined already by the ground state, and you just plot the curve, which is no parameter at all in it. As you can see, from about 2 onwards, neglect this point, which, as I say, I shouldn't really have had. It comes from a different kind of calculation, which is much less accurate. That's why it's got large errors on it. From here onwards, these points here, really, there's very little deviation. There's tiny bit of deviation, but very little deviation. At a sort of percent level, there's some deviation from Nambu-Goto, but otherwise it's extremely accurate. So that's quite impressive just looking at it. It's even more impressive if you look actually at these alternative expressions, which asymptotically, this Nambu-Goto goes to that, and if you expand it to one extra term, you get this. So this is the expectation from the work, the recent work, which says that not only is the first term universal, but the second term is universal. And this is the original expectation that just that this term was universal. If you plot these, this one here gives this dashed line, and this one here gives this long dashes, well, dotted line and dashed line, let's say, which is probably what it is. So, although it's clear that, well, although you could convince yourself that the calculated values will eventually merge with the theoretical expectations from here and here, they're still quite far away. They're sort of significantly far away, even up here, the very longest string we have. And as you go to shorter strings, they deviate considerably. And the interesting thing is, you notice that the leading order term, if you go to shorter strings, the leading order term deviates less than if I include the next order correction. And the reason, so that's a bit odd, but the reason for that is, you can see if you look at this expression here, once I'm down this kind of expression, if I expand it in a power series in 1 over sigma L squared, there's a square root, and if I expand it, it's only convergent if sigma L squared for n equals 1, neglect the 1 over 24th, it's small. For n equals 1, it's only convergent if sigma L squared is bigger than 8 pi. You need an expansion parameter, which is less than 1. And that means that root sigma L is about 4.5, so it's only convergent from here onwards. From here onwards, if I was expanding this and including higher and higher order terms, I would start getting predictions which will go wildly oscillating, and you lose it. So this is already saying that power expansion of this kind is not going to capture the fact that you're doing so well with Nambu-Goto, because it's failing to converge below here. So that's again an interesting, I think, observation. Nambu-Goto is working extremely well. There are deviations from it. Here, I should say, our calculations are getting a little bit iffy. It's getting hard to extract the lightest mass. The correlation function sort of, it's hard to get good overlap onto the operators, basically, for these very short strings. And maybe we could do better, because our whole intuition when we set up our operators was based on thinking about wavy long strings, and that's becoming perhaps inappropriate here, and that's why our operators aren't very good. So here our calculations are beginning to get rather bad, but definitely whatever the mass is, it's less than this. It's less than equal to this. I mean, to the extent we have extra errors, they will bring this down. Here it is certainly reliable. So, so that's actually an interesting extra piece of information that shows that Nambu-Goto is working remarkably well. So that was SU3, and also SU3 at 2 lattice spacings, and so that we see that actually that's a statement about the continuum. What happens when we increase n? Well, actually, pretty much nothing very much. This is SU6. The red points are now SU6. The blue points are SU3, and we didn't do the SU6 calculation to such small lengths. We started at around 2, but from there onwards, they're almost the same. Actually, if one was going to say that there's any difference, the SU6 seemed to deviate a little bit more from Nambu-Goto than the SU3, but that could be partly that maybe the SU6 calculation was a bit harder because it's slower, it takes more time. Well, I don't know if that's significant. But anyway, there again you have a very, very close agreement with Nambu-Goto down to remarkably small lengths. So that was the first excited state. And the first excited state is just a single state. One of the interesting things with Nambu-Goto is that as you go to higher excited states, you have degeneracies. And you have degeneracies because, well, for various reasons, these phonons don't interact with each other. So that if you if you have a state like this, or a state where you create something with twice the energy, these will be degenerate in Nambu-Goto. So as you go to higher excited states, you start having degeneracies. And then also, under parity in 2 dimensions, the fluctuation changes sign. So since the fluctuation is expressed in terms, classically in terms of these A's times eta or whatever, these under parity, A goes to minus A. So negative parity, there are negative parity states which have an odd number of creation operators, while the even parity ones have an even number of creation operators. So at some point as you go up in the excitation, you start seeing negative parity states. that's a new set of states you can actually look at. The number one, they're degeneracies, which are interesting when you go to higher excitations, and also negative parity states. So that's a motivation for going, one of the motivations for going to at least one more set of states, which I'll now show you in SU3. The slides get more messy as we go. In some sense, there are more points as we go, include more states. So now what I've shown you here, so this is the ground state that I originally showed you some time back now. Well, actually, I didn't show it to you for this SU3 calculation, but here it is, with a Nambu-Goto going through it. From that, we can extract the string tension. Then here's the first excited state, which we just spent some time looking at, all by itself. I've now normalized the energy by a different, not by sigma L, but by root sigma. So now these points, instead of coming down this way, as they did before, are going up. I'm sorry for that. It's a kind of, I'm confusing you by presenting the energies in different units. Before I divided the energy by sigma and L. Now I divided just by square root of sigma. So there is a rise now that you can see at large L. That hasn't been factored out. Okay, so this is what we were just looking at a moment ago, and that is a single non-degenerate state. And then we go to the next set of states where there are four states. And that's essentially, because these have zero momentum, you have to have left and right as well. Before I can check that I have this down here. I might as well show you the sort of content of these states without writing it down each time. Here are the various excited states. At the moment, we're looking at Q equals 0, the zero momentum one, so the ground is ground state. Then there was this one is the one we were just focusing on. Well, when I say we were focusing on it, I calculate some excited state, and then I compare it to Nambu-Goto. In Nambu-Goto, this is the spectrum. I don't, of course, know directly that my state corresponds to that. As you saw, it fitted very well in terms of the energy dependency. So this was the first excited state for Q equals 0. And then I'm now looking at these four states, which are obtained by having K equals 2 left and right, or 2K equals 1s going right and 1K equals 2 going left, or K equals 2 going right and 2K equals 1s going left, or then just 4K equals 1, 2K equals 1s and going right and 2K equals 1s going left, two phonons of these momenta going right and left. And these here you have an odd number. For these two, you have an odd number of these creation operators, so that's negative parity, and these are positive parity because they have an even number. So there are these four states that you have in Nambu-Goto. And indeed, we find four states when we do this lattice calculation that do become degenerate at large L, and are pretty degenerate until about L root sigma is 4. They look like being slight deviations here, but they're beginning to be at the level, these are quite heavy excited states, they're beginning to be at the level where I wouldn't be certain whether these deviations for this excited state were real or whether they were a product of our uncertainties in our procedures. But then you definitely have a splitting, and the splitting is not just, doesn't seem to be random. The positive parity one of the positive parity states goes down, one of the negative parity states goes up, and then one negative parity state and one positive state really stay on top of Nambu-Goto right down to the shorter strings. So this is presumably telling you something and about the way these phonons are interacting with each other. But you need a framework in which to discuss that. And I don't really have a framework, but some of you may have, so I'm telling you about this. Maybe some of you will have ideas. So I have a framework about a free string. My framework is a free string theory because that's relatively trivial. But going beyond that and understanding these deviations from free string theory is something I'm not quite sure how to do.
You don't have any way to know which linear combination of those states is splitting which state.
Not directly. I'm not. I didn't really think about that. This is all very recent work in a sense. Part of it is very recent, and I haven't really thought about that. I haven't really thought about whether it's possible to know that or not.
They have the same quantum numbers.
They have the same
all
quantum
numbers are the same.
Yeah.
So it seems unlikely.
Yeah, it seems unless you can see something in the operators that reflects. But I'm not sure what different occupation numbers
They
do
have
in
different
operators.
left-moving excitation, for example.
Yeah, but my operators, they're these fuzzy operators with just, it's very hard to read from that. So I'm not sure. Yeah, I don't know. I'm certainly going to think about that. And maybe there's something, maybe there's some clever way one can actually read off or decide from the lattice operators, because I do have the lattice. I have my when you do this variational calculation, you end up with some operator which is the best operator in your basis, and usually a pretty good operator, like 95% overlap onto some particular state. So I have a lattice operator in terms of lattice variables, which has a 95, which is a wave functional to a good approximation for these states. The question is whether I can read off from that messy thing, which is a linear combination of various other lattice operators, whether, what excitation numbers there are, and I'm not sure about that. That sounds to me quite tricky. I think it's not obvious anyway. So, as far as this excitation spectrum is concerned, once again I could show you some results from a smaller lattice spacing in SU3 and SU6, and nothing much changes. So, what I've shown you there is really what you see both in the continuum limit of SU3 and when you go to larger N. When you have these, so if you now might go to, there are some states, as I just showed you, which have non-zero momentum. There are these kind of states, which were a subset of the ones I just showed you. And now you don't have a balance between the left and right movers, and so there are extra states here, extra to the ones I showed you, which in particular is a true ground state, the true ground state with just one oscillator. So that has nothing else to interact with, no other oscillator at least to interact with. So there's just one ground, that's an interesting state in itself. And now if you do the same thing, if you calculate with non-zero momentum, and on the lattice the way you do that is, well, you've got some operator for your flux loop, and you have to make it not translation invariant in this. If you're going to have a non-zero momentum here, it must be non-translation invariant, otherwise it would always give identically zero, something identically zero. So you have to give it some kind of, blob somewhere, or something of that kind, something that's, so it's not translation invariant in this direction. And then what you do is you take this one and you add to it the translation in this direction, and you multiply that by the appropriate phase, e to the pi, e to the ip, the momentum times the amount by which you've shifted it. And then you sum up over all translations and you get a non-zero momentum. So for some of these operators we can certainly do that. For quite a lot of these operators we can do that, and we do get results for non-zero momentum. Now you can ask yourself, how does that look compared to Nambu-Goto? Again, there's no fit here because the string tension has been calculated from the ground state. And so these are the first four states as a function of L. Now there's only 3 L's here. What's essentially happened in these calculations is that originally we set out to do these calculations, then we realized that Nambu-Goto was working remarkably well, and then we thought, well, it would be interesting to see the non-zero momentum, but by then we had finished most of our calculations, so we had to go back and do some more, and we only did those for a few L's, and so it was sort of getting more and more focused, the whole calculation. So well, we did it for these 3 different L's, going from 2 to 4, L root sigma and units of root sigma, and you see that you get, again, this is way a much smaller L than you would expect a power series expansion of this to converge, and you get very good agreement for Nambu-Goto, particularly actually for this. There is some disagreement. There is a breaking here. There's no apparent breaking here. And here I'm less sure of this. I suspect that might be an artifact of having a very excited thing in our lattice calculation. Doesn't deal with
the lowest line. You can access directly a one phonon state.
Yeah, so this is a one phonon state by giving, well, I believe it's a one phonon state. That is the Nambu-Goto one phonon state, this line.
Right.
So I'm always cautious about saying it's a one phonon state because what do I know about my lattice states? But this indicates strongly it's a one phonon state. So you do have a one phonon state, and then you have some states with the lowest, yeah, so the lowest, so there's also one phonon k equals 2 state, which comes up here. One of these two. That's also a one phonon state, but with double the energy.
Yeah, it would be interesting to track the one phonon state
Yeah.
as you increase its
Yeah.
momentum to try and understanding the deviations of its dispersion relation.
Right.
and naive
Yeah,
relativistic.
okay. And maybe also to see what happens at lower L for that one phonon state too, because that would be,
Yeah,
that would-
then
yeah.
you'll see the further deviations.
Yeah.
But, I mean,
yeah, but
so
you're saying with
if you go to
dispersion
high
relation.
mode number, you should also be probing
Yeah.
something about the short distance. Maybe.
Yes. In principle, we were going to calculate all momenta because it's sort of trivial, but there were problems with the memory on the computer because you have these huge number of operators, you have a matrix of correlations, hundreds times 100 matrices, and then you start doing it for various momenta, and for some reason the programs were, I think that problem will be solved, but they were crashing at some point through using up too much memory. Okay, so that's just to, I'll stop now in a moment. I'll just show you one, if you like, just summarizing all these particular states I've looked at. So here is the zero momentum and the non-zero momentum, the ground state, the unit momentums thing, which has one phonon, just 3 points here. Then you go up to looking at some of the others, and you see all the degeneracies at larger L. You see all the degeneracies you expect, even among different momenta. So so the picture fits with at least the momentum we've looked at, which is just the lowest momentum, Q equals 0, 1, and 2. So at least at this stage, what I'll say is that, so certainly we had very nice evidence of the universality classes of that of the bosonic string theory. If you look at the correction, 1 over L correction, it looks like it's close to 1, the coefficient, within small errors. But more than that, the Nambu-Goto covariant string spectrum, the energy squared being equal to this, and if you take the energy as the square root of that, that expression works extremely well, way past to shorter strings than to strings which are so short that you can't actually expand that square root in a convergent expansion. So that this is a challenge, I think, to theoretical approaches which are trying to understand high-order corrections. They have to sort of somehow encode this. The fact that the starting point, I really think, is a Nambu-Goto plus possibly small corrections, rather than being sigma L times small corrections. So what I'll do in my last lecture, yeah, I am finishing. Just looking at the clock. What I'll do later today is move on to some other, I'll say something a little bit about strings which are multiply wound. This is a singly wound string. And once you wind more than once, you also have the possibility that you can see something about the way the string interacts with itself. Not the phonons, but the actual string. So if you have a twice wound string, then these flux tubes are there next to each other, and they can interact. So you can learn something. It may become, in a sense, that information is probably there, as people said, you know, if you have arbitrary fluctuations of the string, they can interact as well with themselves here, but it's much more hidden here, while here it will become, you'll have a whole string that can interact with itself, and so it should be more obvious what the interactions are. So we'll be looking at some of those, what are the interactions of strings with themselves, and after that I hope I'll have time to say something about something that's relevant to large N and to ADS-CFT considerations about a slightly different topic, which is hot QCD, or gauge theories at high temperature, at non-zero temperature. So I hope, although I'll start this afternoon with something on strings, I'll then move on to gauge theories at finite temperature. Okay.
questions, comments? Okay, let's thank Mike again.